Okay, today's lesson is on similarity, and we're going to ask ourselves, are figures similar? This covers the Common Core State Standard 8G4. Understand that two-dimensional figures is similar to another if the second can be obtained by the first with a sequence of rotations, reflections, translations. So those three, the series of transformations involving the first three, creates congruent figures, whereas if you add dilations to the mix, it's going to create what we call similar figures. Okay, given two similar figures, can you exhibit a sequence that exhibits a similarity between them? So our vocabulary today is similarity and transformation. So first, let's review the properties that change with certain transformations and those that don't. So with a translation, the position, so the vertices of the polygon have different coordinates. So the position changes for all vertices. The orientation does not change, so how the vertices sit with each other. So if you look at the first figure here and the second figure here, the vertices are all in the same order. Okay, and we went over this yesterday in the lesson, so I'm not going to go over it extensively here, but the orientation doesn't change with translation, nor does the size. Reflection, the positions change unless it's on the line of reflection. The orientation does change, but the size doesn't change. Same with rotation. And the last one, for dilation, the position does change, the orientation doesn't change, and the size does change. So really, dilation is the only one in which the size changes. Okay, it's the only transformation in which the size changes. Okay, and to define similarity, two figures are similar if one is a dilation of the other. When two polygons are similar, any ratio of corresponding side lengths are the same. So let's try to answer this question: Is the blue figure a dilation of the black polygon? So in order to answer that, I'd have to check the ratios of corresponding side lengths. So if they were similar, then this side length, let's put some labels on here. Okay, let's put A prime, B prime, C prime, D prime. Actually, we can't label them with A prime. We can't label them with primes because we're not sure if they're similar. So let's just do this. Okay, so I want to check if the measure of BC, I want to check the ratio of the new to the old. Okay, so let's assume that we started with the black polygon and we shrunk it down to the blue polygon. So that means that the new one is the blue. So let's try to look at some lengths that may be corresponding. So F and G and B and C. Let's look at these ratios. So FG is 2 units long and BC is 4 units long. So that's 1/2. Okay, in order for these figures to be similar to each other, then the rest of the ratios, so the ratio of this to this, the ratio of this side length to this side length, and finally the ratio of this side length to this side length would all have to be 1/2. Okay, so let's just check that. Let's start with the red. Okay, so in the new one, EF is 2 units long, and AB is 4 units long, so okay, that's 1/2, that's good. All right, let's check the green size I labeled green. This right here, well actually this is a little trickier because it's, we'd have to use the Pythagorean Theorem to find out what that side length is. If I have a right triangle, I have one unit there and 2 units there, then this right here would be 1 squared plus 2 squared, and it would be the square root of that. Okay, so it would be the square root of 1 plus 4, which is the square root of 5. Okay, so that's this one right here, that's the square root of 5. Now for the larger triangle, let's see what we got here. We have 2 along this side, and we have 1, 2, 3, 4 along this side. So this side would be the square root of 2 squared plus 4 squared, which is square root of 4 plus 16, which is square root of 20. Now, the square root of 20 I can also rewrite as the square root of 4 times the square root of 5. We're going to learn this a little bit later on, so you'll just have to take my word for it for now. But the square root of 4 times 5 is the square root of 4 times the square root of 5, which is, this right here is 2 times the square root of 5. Okay, so in fact, if the new one is square root of 5 and the old one's 2 times the square root of 5, that ratio is 1/2. So if I put the square root of 5 over 2 times the square root of 5, well, these just cancel, and there's a 1 remaining here. So those, again, these side lengths are, the ratio is 1/2. And similarly, you'd find with the blue, right? So the blue is, this is 3 over 6. So 3 over 6 is also 1/2. So checking all the sides, this is one way to check to see if things are similar. If I check each polygon and I say if the side lengths are all the same ratio, then they are similar to each other. So we can say that polygon ABCD is similar to polygon EFGH. Okay, and the symbol that we use for similarity is just one squiggly line. So if I could say that ABCD is similar, that's what we use, to EFGH. That little symbol means similar. Okay? Okay, so I could be asked the question, like I was before, are these two figures similar? So it is a triangle ABC. This is my question. Is it, and that's the question right there, is it similar to triangle XYZ? Okay, so in order to figure out if it's similar, almost the same thing for congruency, we have to see if there's a sequence of transformations. This time we can include dilations that make one figure lie on top of the other. So this picture right here is from the textbook. So if you ask, are these two things similar? Well, the first thing that they did was they rotated ABC. In the next series, they rotated ABC. Looks like they rotated 90 degrees clockwise. And then, so it's a 90 degrees, counterclockwise rotation, followed by a reflection over the y-axis. Sort of getting in. And then it looks like a dilation. So it looks like a dilation of 2. Let's just check this out. So this side length was 2 before, and now it's 4. This one was 3, and now it's 6. Okay, and since that's a right triangle, we can say that that is a similar triangle. Okay, so the answer is yes, they are similar. How do I know that? Because there's a series of transformations. A 90 degrees rotation, followed by a reflection over y-axis, followed by a dilation of a factor of 2. Okay, so let's just ask ourselves this final question. If quadrilateral QRST has these vertices and JKLM has these vertices, we have to determine whether or not they're similar. So I'm going to pause the video and graph these two and get back to you. Okay, so I've just graphed these two figures here, and I'm going to ask myself, are they similar? So it looks like they sort of appear to be facing in two different directions, so that's probably some result of a reflection. So let's just take one of these points, like Q1, 1. It would appear that it looks like it would be similar to J, or it would be that J might be the image of Q under a series of reflections. So J is -2, 2. Now again, can I find something what can I do to Q in order to get to J? So it looks like it's been reflected over the y-axis. So let's see if we do that. That would be -1, 1. And then you know what? It's probably followed by a dilation of 2, which gets you the -2, 2 that you need. Let's try it with another one. It looks like R might be associated with K. So if I reflect that over the y-axis for a minute, that would be -3, 1. And if then I dilate it by a factor of 2, that would be -6, 2. Does that get me K? And it does, right there. So let's just visually check. If I take S and flip it over the y-axis, that would get you negative 4, 3, and then I double both coordinates, it gets me that, and the same thing there. So the series of transformations was reflect over y-axis and then dilate by 3. And I bet you could even do that in the other order. If I dilated this by, 2 and then reflected it over, it would be getting the same thing. Dilate by a factor of 2. So to answer the questions, are they similar? The answer is yes, because I can find a series of one of the 4 transformations in order to get this blue figure on top of the purple figure. So we can conclude that that QRST is similar to JKLM. Okay, and that's the end of the lesson today.